Hello, this is Math Jazz from Almost Cool. This is the first of our videos in our series of videos on derivatives. The topic of this video is the definition of the derivative and some properties of the derivative. Here is the definition of derivative. It's an equation, and on the left-hand side of this equation we have defined the symbols that we will use to represent derivative. That is f prime of x. So that's the derivative of f at the point x. On the right-hand side of our equation, we have an expression that will calculate this value. That is, the limit as h goes to 0 of f of x plus h minus f of x over h. Now the intuition of this is that the derivative will tell us the instantaneous rate of change, or the instantaneous slope of a particular function, in this case f, at a particular point, in this case x. This concept comes from the following expression, which gives us the average slope of a function over an interval. F of x2 minus f of x1 divided by x2 minus x1. That is the difference of the y values divided by the difference in the x values. We can rewrite, as on the right-hand side of this equation, if we let h be the distance between x1 and x2, so x2 minus x1, and if we let x be x1. So now we have this relationship between average slope of a function on an interval and this this difference quotient here, f of x plus h minus f of x over h, which is the fraction in our definition of derivative. To continue, let's build up the graphical representation of the derivative. We're going to start by talking about something called a secant line. A secant line intersects a graph at 2 points. In this case, it looks like we intersected around 0.7 and 2.9. The particular points of intersection won't matter. What we will care about is that this is the secant line that for the function f between the values x1 and x2. Now the slope of the secant line gives us the average behavior of the graph between the points it intersects the graph. That is the average slope of the function between these 2 points. If we label these 2 points of intersection x1, y1 and x2, y2, then we can use our normal expression for the slope, and we can use those substitutions, substituting f for y and substituting h for the difference between x2 and x1 to get a relationship between the slope of the secant line, the average slope of the function, and that fraction in our expression for the derivative. And we'll do this like so. H is the distance between x2 and x1, as said, f represents y, and these are all the substitutions performed. Using equations, here are the relationships between m, the slope of this line, and between the average slope of this curve. So m equals f of x plus h minus f of x all over h. So if this is an approximation, this is the average slope over an interval, then obviously as we let that interval get smaller, we will get better approximations of the slope of the function at that point. Oh, for people that love words and the history of words, this line is called a secant line because it cuts across the graph of the function. Secant comes from the Latin word for cut. Now, secant is also the name of a trigonometric function, and if you go to our trigonometric function videos, you'll see that on the old ancient definition of secant, the secant is defined as the length of a certain line segment, and that line segment actually will cut across a circle. All of these trig functions are, of course, defined in their relationship to a unit radius circle, and the secant is the length of a particular line segment that can be drawn on the circle. This actually is also the origin of the word tangent. The tangent function comes from the length of a particular line segment that touches the circle at one point. And the word tangent comes from the Latin word for to touch. So the secant line hits the circle in two places, therefore it cuts across it, and so it is a cutting line, a secant line. And the tangent line touches the circle in one place, it touches it, and therefore it is called a touching line or a tangent line. And the tangent line of a function at a point has the same slope as the slope of the function. So we say that the derivative of a function is the slope of the tangent line at that point. But we are getting a little ahead of ourselves. So for one thing, I said that shrinking the interval, shrinking h, gives better approximations of the instantaneous slope. I should have placed a caveat on that. Not all functions have derivatives. The ones that do have derivatives are called differentiable functions. And for those functions, reducing h, that is reducing the distance between x1 and x2, will create better and better approximations of the tangent line, the line that touches f at one spot and has exactly the same slope as the function does at that spot. But there are functions that are not differentiable. These limits do not exist, the derivative cannot be computed, and we'll get to those later. But for differentiable functions, that is, functions that have a derivative, this limit exists, so secant lines can be used to approximate the tangent line. In fact, if algebraically what we're doing is taking a limit of this algebraic expression to calculate the value of the slope of the curve, then graphically we are doing the same thing. We are taking the limit of secant lines as the second intersection point of the secant line approaches the first point being the point where we're trying to compute the slope of the curve. So here we have our graph of the tangent line. This is a nice example of it. Here's our function, here's the tangent line. Notice that the curve of the function is going in the same direction as the tangent line at that point of intersection. So this is called the tangent line of f at x. Because, of course, if we picked a different point, we would get a different tangent line. If we picked a different function, we'd also get a different tangent line. So this is the tangent line to f at x. And we'll approximate this using secant lines fairly soon. Because we can't actually compute this thing directly since x1 and x2 are equal to each other, so that means that in our slope function y1 minus y2 over x1 minus x2, we get a 0 in the denominator, so we can't find that unless we use a limit. So using algebraically, that's the limit of that difference quotient, and graphically it's the limit of secant lines, and we will do this graphically here. So we have our function, it's the blue curve, and we have a secant line, that is the red curve or the maroon curve, or if some art major could tell me what color that is, I'd appreciate that. Anyway, this secant line touches the graph at 2 points. We are going to approximate the tangent line at the left point of intersection, which means that we'll have to move that right point of intersection closer to the left point of intersection. This is not a good approximation as we have it. Our x1 and x2 are too far apart. That is, our h is too big. We know the slope of the red line is positive and the slope of the function at the point of interest is negative, so it's not a good approximation. But as we move this point closer, we will get better approximations. Notice that the yellow line, or the gold line, is 0 slope, and that h is a smaller value. That is, the distance between these 2 points of intersection is smaller, and instead of having the wrong sign, we just have a 0 instead of the correct sign. The green line is better because it has a negative slope, and the function obviously has a negative slope. And again, we obtain that by shrinking h a little more. As we continue to shrink h, I'm going to have to zoom in on the picture because it's going to get a little crowded with the lines that we're drawing, but we'll zoom in and add a fourth line, and we see that's an even better approximation. The light blue line is a better approximation of the dark blue function curve than either of the three previous lines because we've shrunk the distance again. And we'll zoom in again and we'll add another line. See how the purple line almost completely covers the dark blue function? That's getting to be a fairly good approximation. And again, as the limit, as h goes to 0, this limit will become the tangent line, which oh, did I do another line? No, that's still the same 5 lines. Anyway, but as we continue to get closer and closer, smaller and smaller h values, closer x2 to x1, we'll get a secant line, a good secant line approximation of the tangent line. We'll get the tangent line in the limiting case. So here's another picture of a tangent line, just to kind of resolve that chord. You know, the tension was building as we were getting closer and closer secant lines to that tangent line, and now this is the resolution. We have a tangent line, so that's good. And we now have to talk about non-differentiable functions. Not all functions are differentiable, and the ones that are not differentiable, the limit doesn't exist, and shrinking h does not give us better approximations of the instantaneous slope. There are a few ways that this can happen, but for all of these functions, the commonality is that the idea of a slope doesn't exist at that function at that point. We're going to give an example of a function that has a sharp corner. This is a function that does not have it's not differentiable at a point. In particular, that sharp corner is not differentiable, and we'll show why this is not differentiable using secant lines to approximate our tangent line and showing that it just doesn't work. Now, there are other types of non-differentiable functions, but this was easy to draw. So we will show again that this sharp corner is not differentiable. Here are some approximating secant lines of this function at the point 2 where that sharp corner is. I did flatten the graph a little bit so that I could draw these lines, but the red line is, of course, our first secant approximation, and as we move x2 closer to x1, where x1 is that of the sharp corner, we see that we're getting slopes that are more and more negative as we go on. And so that would lead us to think that if there were a tangent line, it would have a negative slope. Unfortunately, the definition of derivative requires a two-sided limit. And so approximating from the one side, like we did for the previous example, isn't everything. We have to approximate from both sides. And on our differentiable example, it just happened that it's differentiable, so the approximation from both sides exists. You could go draw some lines on the previous picture and see that the limit, in fact, does exist from both sides. But on this particular example, this example of not being differentiable, we'll look at the left-handed limit, and as we're approximating on the left-hand side with these secant lines, we notice that the secant lines are getting more and more positive slope as h is coming closer to 0. So from the right-hand side, we have a negative slope getting more and more negative, and on the other side of the function, we have a slope that's positive and getting more and more positive. And so this limit can't exist. And because this limit doesn't exist, the derivative doesn't exist. So, and again, there are other examples, but this was a fairly easy one to draw. So, since the derivative is defined as a limit, though, we obtain some properties about the limits. So, We're going to eventually prove a lot of derivative rules. These derivative rules will allow us to compute the derivative much easier than using the definition of derivative. But most of the proofs of these derivatives rely on skillful application of a limit law. And so we'll talk about just a couple of properties of derivatives, and we'll leave most of the derivative rules to other videos. But to start off with, we're going to talk about how derivatives are linear. That is, they have linearity. The definition of because the derivative is defined as a limit and inherits linearity from limits. Linearity means that we can split, if we're taking the derivative of some expression, we can instead take the derivative of each of the terms of the expression and then add them together. And by doing that, we can, instead of taking the derivative of a gigantic expression, we take the derivatives of each of the parts and we add them together, and it gives us the same answer, but it's sometimes easier to work with. Also, this allows us to factor out constants. So, as we see in the statement of linearity, if a and b are constant real numbers and f and g are real valued functions, then the derivative of a times f plus b times g is equal to a times the derivative of f plus b times the derivative of g. So this is a very useful property, and it seems trivial. Like, you might look at that and think, oh duh, it should be that way. But there are lots of things that we use that are not linear. They do not have linearity. In particular, squaring something is not a linear procedure. So the square of x plus y is not the same as the square of x plus the square of y. They're different by a term 2xy. And you can multiply that out yourself if you'd like. But anyway, since we have examples of things that do not have linearity, then it is actually an interesting property, and a very useful one at that derivatives have this property. And we will now prove that derivatives, in fact, have linearity. So we'll assume a and b are constants. We'll assume f and g are differentiable functions. The definition of derivative is given by this. That is, the derivative of a times f plus b times g is equal to the limit as h goes to 0 of a times f of x plus h plus b of g of x plus h minus a times f plus b times g all over h. So that's a long equation, but it's just applying the derivative definition to this expression here. Now the right-hand side can be rewritten as follows. This is just, we are going to switch the bg of x plus h term with the negative a f of x term. So we get all the f's on the left side and all the g's on the right side. We're going to split the fraction in two because we can. And then we're going to factor an a out of the f fraction and a b out of the g fraction. It's all algebra. And if you want to, you can pause it and work it out on a piece of paper. Pause the video and work this out on a piece of paper. Once we have this, though, we know that limits have linearity from a previous video, which I'll actually make in the future, but you can watch it before this one if you want to see the proof of that. But limits have linearity, and that allows us to break apart the fraction, take the limit of each fraction, and factor out the a and the b from each of these fractions. So we get that we have a times the limit as h goes to 0 of f of x plus h minus f of x over h. That is a times the definition of the derivative of f. And we have b times the definition of the derivative of g. And so we use the definition of derivative to replace those two things with f prime and g prime. So what we have is exactly the relationship we wanted. The derivative of a times f plus b times g is equal to a times the derivative of f plus b times the derivative of g. And we fit it on one slide. So that was actually pretty nice, being able to just fit it all in one sheet of paper. or one screen on the computer. But that is the proof of linearity. Another property we're going to talk about before we wrap up the video is differentiable functions are continuous functions. So first we're going to suppose that f is a differentiable function. Then we know by the definition of derivative that this equation is true, because otherwise f would not be differentiable. Now if we multiply both sides of the equation by the limit as h goes to 0 of h, we get the following expression. F prime of x times the limit as h goes to 0 of h is equal to the limit as h goes to 0 of h times the quantity f of x plus h minus f of x over h. We get that because the product of two limits that exist is the limit of the product. And since we have a differentiable function, the limit of the derivative exists, or the limit of the difference quotient exists, and we know that the limit of h as h goes to 0 is 0. Those two limits exist, so we can combine those two limits, and we get the expression we have on the far right-hand side of this string of equalities. Well, we notice that the h's will cancel on the right-hand side, and we notice that the limit as h goes to 0 of h is 0, and so whatever the derivative of f is, that times 0 is 0. So the left-hand side of the equation is 0, and the right-hand side of the equation is this limit here. So we have 0 equals the limit as h goes to 0 of f of x plus h minus f of x. And that shows that f is continuous at x because it shows that the limit of f at the limit of f at x is equal to the value of f at x. So that's the definition of continuous. So all differentiable functions are continuous. And I'd like to thank you for watching this video. Feel free to email suggestions on future topics for videos, to ask questions, or inform me of errors in the video, or for anything else. I hope that you are enjoying learning about calculus. I love calculus myself. I think it's such a beautiful subject, and I know that it is hard, but it is very rewarding. And I wish you the best of luck in learning this material, and I hope that you can feel the joy of looking around the world and seeing the calculus that is in it, and seeing how your perception of the world can change having these extra tools of calculus. I hope that you have a great day. Again, good luck and goodbye.